Hi, welcome to next topic, chemical kinetics. Today we are going to discuss the um, second order reactions and write equation for a second order reaction. As we already discussed what is order of a reaction, and there are different types of first order, pseudo order, second order, third order reactions are there. And if a reaction is said to be second order, then this rate of a reaction, that is R is equal to K2 into Ca into Cb. The power of the concentration time is equal to 2. And that's why this kind of reaction is said to be second order. Or it's another way we can written as K2 is equal to C square, or K2 is equal to Cb square. In all these equations, the power of the concentration time is equal to 2. So this kind of reaction is a second order. Then consider the general reaction, that is 2A gives product, that is R is equal to the rate of reaction, that is R is equal to minus d Ca by dt is equal to K2 into Ca square, where C is the molar concentration of the reactant at given time t. If the concentration maybe refer to two different reactants. Here in only one reactants are there. Another example is if there are more than one reactant, there is two reactants are there. That is A plus B gives product. In that particular case, the rate of the reaction, that is minus changing concentration, fall in concentration A with respect to time, that is minus dCA by dt is equal to minus dC, changing concentration of B with the respect to time, minus dCB by dt is equal to K2 into Ca by Cb. That is the rate equation if more than one reactant, that is A, generally we can represent A and B, the rate equation is equal to R into K2 into C, Ca into Cp. We shall going to derive the rate of the reaction on these two conditions, two cases, if there is only one reactant or if there are two reactants. It is the case one when there is only one reactant. It is generally 2A gives P. The rate of this equation is R is equal to minus dCA by dt is equal to K2 into Ca square. That is equation number 2. Rewriting the equation 2, we get that is dCA by Ca square is equal to K2 into dt. That is equation number 3. If we already derived or discussed in the case of first order reaction, that is in general, same thing we are doing in here also. That is, if take Tc0 is the concentration of the reactant at the commencement of the examined reaction, that is at the time t equal to 0, and C is the concentration at a given time t. That is, we are integrating, we are taking two conditions, two limiting condition, that is C0 initial concentration and C is the at the time of the t. Then integrating equation 3, we get integrating equation 3, we get integrating equation 3, that is minus integration C0 to C dCA by Ca square is equal to integrating C is equal to 0 to T K2 into dt. We get 1 by Ca, that is integration of dA Ca by Ca square is equal to 1 by Ca C0 to C with the limit K2 into T. It is 0 to, that is T minus T0, also that becomes T. So rearranging this equation, 1 by C minus 1 by C0 is equal to K2 into T. From this, rearranging this equation, rate constant, second order rate constant K2 is equal to 1 by T into 1 minus 1 by, into 1 by C minus 1 by C0. Equation 4. This equation, the rate of a equation 4 is the equation 4 is the rate of the reaction. Equation 4 is the rate equation for a second order reaction involving is the case one, only one reactant. Then you can usually written on the usual another form, that is A is A mole per decimeter cube is the initial concentration and X mole per decimeter react at a time t. As after time t, X moles of the reaction part of the moles of part of the molecule undergo reaction, and the concentration at time t become A minus X. Then what is the initial concentration, that is C0 become A, and at the time of T the concentration become A minus X. Substituting these values, A instead of C0 and C, A and A minus X respectively in equation number 3, equation number 4. Equation 4 becomes K2 is equal to 1 by T, 1 by A minus X minus 1 by A. Then taking common, that is rearranging this equation, 1 by T is equal to A into A minus X, that is A minus of A minus X, and equation becomes K2 is equal to 1 by T X into X whole divided by A into A minus X. That is the equation number 5, and that is the right equation for a second order reaction. In the case, there is only one reactant. Then case 2, when there are two different reactants, as consider general case A plus B gives pre. Here two reactants are there, different reactants are there, A and B. The rate equation in this case is given by R is equal to minus dCA by dt is equal to minus dCB by dt is equal to K2 into concentration of A into concentration of B. Rearranging this equation 7, we get K2 into dt is equal to minus dCA divided by concentration of A into concentration of B, that is equal to minus dCB into concentration of A into concentration of B. Integrating this equation 8, we get by a method of integrating equation 8, a method of partial fractions, we get, not going to the details of the integration, it is K2 is equal to 1 by C0 A minus C0 B, that is initial concentration of A minus initial concentration of B into T ln Ca into C0 B divided by Cb into C0 A. It is equation number 9, that is the second order equation involving two different reactants of A and B. So, the equation is rewritten in the form of A and A minus X or B and B minus X form, where it is K2 is equal to 1 by A minus B into T ln B into A minus X divided by A into B minus X, where A is the initial concentration of the component A and B mole per decimeter cube is the initial concentration of component B, and X mole per decimeter cube is each of A and B react at a time A. So this equation is valid A greater than B. If B greater than A, the equation becomes K2 into 1 by B minus A into T ln A into B minus X by B into A minus X. Question number 11. And 10 and 11 is applicable if A equal to B. That is the rate of second order reaction is there are two reactants A and B. Then next is units of K2. Your units of a second order rate constant. The unit K2 is equal to decimeter cube mole raised to minus 1 and centimeter raised to minus 1. Both the cases, so case 1 and case 2 units are the same. Decimeter cube mole raised to minus 1, centimeter raised to minus 1. For a first order rate constant, it is second raised to minus 1. Second order rate constant, it is decimeter cube mole raised to minus 1, second raised to minus 1. From the rate constant units, we can differentiate the reaction as a first order, second order reaction. That's the importance of the units of second order reaction. These are some examples for a common second order reaction, that is conversion of ozone into oxygen at 100 degrees Celsius and saponification of esters. So the examples for a second order 8 equations. That's all about second order rate equations. Thank you.